So my talk today is about signal and sound processing capabilities in Mathematica. And we will have also a quick look, mainly a quick look of what's new in Mathematica 10 in terms of signal and sound processing. So just to start slowly, I will present we have a lot of new functions to access data sources. We have a lot more data sources in Mathematica 10 respect to Mathematica 9. We have extended our filters capabilities to work with new objects. And we have introduced two new sets of functions. One is peak detection and baseline detection. The second one is really huge, is array resampling. Basically, we have extended capabilities of image resize, with what was taken resampling argument, to n-dimensional arrays. And the last one is an application examples, should be a little funny, I hope. So new sources, these are the data sources that were available in Mathematica 9. It's already something, but in Mathematica 10 we have more, we have much more. Oh, why is it so big? Basically, the huge plus is, of course, Wolfram Alpha. We've been working a lot on data sources for Wolfram Alpha, and you can access all of those from Mathematica 10 using, many of them can be accessed as one big function like entity data. You specify your entity like France, and you get a population, or you specify a city, you get like weather properties, all with entity data. But we have many wrappers to like simplify your code. And here are like some non-exhaustive samples of what you can get. For example, you can get weather data from weather station, or in this case, it's air temperature data. This is one of the wrappers I was talking about. You can create like infographics, also constantly updated infographics, and deploy them on the web. This is wind map of the USA. I wouldn't try this with hotel internet connection. I will get some data later, but you have, of course, financial data. And you can get all kind of stocks, market data, dividend data, return value. This was more selection. Extended filtering. So we had always had filters for images, for data. We have this sound object in Mathematica. For example, here, this is a sound. Should play, let's try.
An iron curtain has descended across the continent. Behind that line lie all the capitals of the ancient states.
So this is Winston Churchill, and this is a sound object. Now you can feed this sound object directly into Mathematica filters. I think many of them, even if not all of them, support sound objects. This is, the one that makes sense with the sounds. This is a bandpass filter. The band is roughly around what you would use to filter human voice. And so this is the new Churchill with a bit less noise. I don't know if you can hear it without.
That line lie all the capitals of the ancient states of Central and
You can
Eastern
see
Europe.
here we have. We will improve this sound interface. I promise. We had the periodogram on top, and you see like here clearly you see the band cut. Below it you don't see so much, but anyway. And then we have time series in Mathematica. I think we had already Mathematica 9, but the framework has been expanded a lot, and it was time to make our filters compatible with time series. Right now we support only regular time series. We are actively working to support all kind of time series in the proper way. I would like to say that we will have support in already maybe Mathematica 10 and something, 10.1. Otherwise, definitely Mathematica 11. Every filter will support irregular time series data. But if you want to use a time series, you have this option here, temporal regularity. So if you already know, for example, you have financial data, and those data are, of course, during the working week, and you can live with the fact that they are regularly sampled because you don't really have data on Sundays. So you can always specify temporal regularity goes to true, and this you can see here. You have this where it is. regular is true. And with this little trick, oh, I have to reinitialize. No, it's okay. You can use the function with the filter. So we have date list plot to visualize the data, and you can just use, for example, mean filter of the data here. It was out of the box. Then let's go to the new functions a bit. Oh yeah, I have time. Peak detection. So we decided it was time to add peak detection. Right now it works with 1D arrays. Of course, the goal is to extend it to work with n-dimensional arrays. It will come. So let's get some data from, for example, Google, and let's see. So this is find peaks out of the Google Stock Exchange. Why not every peak is highlighted? Because this is the default find peak. It will just choose a suitable sigma scale at which to look for the peak. And we see that not every maxima is revealed. So what can you do? You can, of course, go to scale 0 and get all the local maxima in the signal. Of course, why we have default scale? Because if you get a longer time series, this is like 4 years, and you do this, it will be useless. So let's select just the peaks that survives a Gaussian blur of 5 days, more or less. So you get something that's just a bit more useful. And of course, you have also more parameters. This is like interactive version just to demo to you the functions. So you have scale parameter that will basically control the Gaussian scale at which you are looking for the pixel. It will blur and will check the pixel survives, is strong enough to survive. That's Gaussian blur. Sharpness parameter, it will be a condition on the sharpness of a peak. It's a condition on the second derivative. So you can get just the sharpest peak or all of peak. It's up to you. And threshold is a hard threshold. So, for example, you don't want the peak at the bottom. You have in this data set, it's not so useful, but you may, of course, want to specify a threshold. Other function. Oh, we have just I mentioned to you is not much different. This function is called find peaks to mimic max detect and min detect. We have also a function called peak detect that will return a binary array. So if you are just interested in like is a peak or it's not a peak, you can get a binary array with peak detect. Another function we've introduced is estimated background to give a rough estimation of a baseline of a data set. So let's get again temperature, and let's get the background. So this is a baseline. So how do we use this? Let's take away all the quantities from this so we can do a bit of subtraction and addition. So here we have basically right now 2 methods in this function. One is statistics sensitive peak clipping, which will try to avoid clipping the peaks while averaging in order to get the baseline. And the other one is just moving average if you just need something simpler and, of course, faster. So we can work different scales. Of course, at scale 0, you have your signal. And here on the bottom, you see the subtraction from the baseline subtracted from the signal. So increasing the scale, you can fine-tune where your baseline needs to be. And you see here that the peak-sensitive background, it will avoid averaging in the peak region, while the mean gauge, I mean, you know what it is. The second parameter is for this orange line with the statistics sensitive peak clipping, and it will basically control if you want let's say farther degree of smoothness. This is like bounded to stay below the data set. But let's say you have some noise at the bottom. It's not like a clean baseline, so you can allow for some smoothness, and you can basically allow this to penetrate a bit into the data set. So it's controlled by this second parameter. And so this is what we have with estimated background. The big thing in Mathematica 10 for sound and signal processing is array resample. So array resample supports different resampling schemes. You can resample by points or by intervals. You can specify where the center of your interval will be. And of course, you have a lot of different resampling kernels. Sorry, this shouldn't be here. So array resample supports natively, not naively, was spell corrector here, natively, many resampling kernels. Basically, I don't know if we've extended a bit because it was Marcus behind this function, but I think at least all the resampling kernels that were available in the resampling option for image resize are supported. I think some more was added, but I wouldn't bet on this. So here, for example, is a small selection of this resampling kernel just plotted here. And using these kernels, of course, you obtain different results. Here are the simple signal, which is a blue one, which is resampled, I think, 1.5 times. Of course, you can specify the dimension of your final array, or you can use scaled dimension if you want, like double the length, half the length. So let's see some option here. We can resample data. Let's get again our temperature. Oh, no, we don't need this. We need this. So here I'm taking the temperature and I'm taking the date list plus. So I have two data sets, but unfortunately one data set is measured day by day. The second data set is measured week by week. So what do we do? Array resample doesn't yet work with time series right now. It's just data array. So I take out the values from the time series and I take out the units. And so if I do this to work with the data set, to do like arithmetic operations or whatever you want to do analysis on the data set, you of course you cannot work with this. So with array resample, you can have the downsample, the higher frequency data set, or you can of course upsample the lowest frequency data set. And this works also on 2D data, of course. This is also n-dimensional data. N-dimensional is a bit difficult to show here. So I will just import elevation data for a mountainous region. And this is like roughly 1200 by times 1200 points data set. So this may take a while to plot. I just scale this by a factor of 1/5, and I do a relief plot. Now, if I check here, this relief plot was done in 0.13 seconds, while the other one, of course, would take more. So this was one small application example for array resample. And I think I have a bit more time here, 5 minutes more. So I prepared, oh no, sorry, I have one more. Yeah, array resample works with sounds. Yeah, I forgot about this. So you may know this.
I'm afraid I can't do that.
Why so slow? Again, well, okay, this was HAL from 2001 Space Odyssey. So this unfortunately is 8,000 hertz, this signal. So I want to upsample this a bit because maybe my other sounds objects are like sampled at a more proper rate. Like let's say here a target rate of 44,000 hertz. So I will specify target rate, and I will upsample the dataset using linear resampling.
I'm sorry, Dave.
Oh, this is wrong.
I'm afraid I can't do that.
Or I can use a maximal order millimole support kernel, and this is kind of order 5. We can go up to 7.
I'm sorry, Dave. I'm afraid I can't do that.
And you will get different result. So this is what we have about array resample. Just to conclude with a light note, I say, okay, we have sounds. Let's play with songs. Why making music with a chain? Okay, well, somebody could say making noise with a chain, but this is not a normal chain. This is a Markov chain. So I'm just this small experiment that I try to do is let's get some single instrument track. For example, this is a piece of Bach for cello. You can get some data, so it's solo cello, string ensemble. You get the most important one is tempo here. We get the song. Let's try it. So maybe have to play this. I think it's something like this. No, something's a sound. Hello. Yes, you may know this. Does it work? No. This is just a MIDI file. It's something pretty simple. We won't listen to like 900 seconds of song, of course. Let's get out the basic time here. Let's try to round it a bit because we want definite states to train to define the Markov process on. So I will just round a bit. The error is I think it's just a float error or basically precision error here. So if you scale a bit more, of course we have bigger error, but I think we can just do with many intervals. So we rescale the songs, Unfortunately, importing the MIDI will it has implicit poses, so it will like the pose will be the end of one node and the beginning of the other with different timestamps. I want this explicit because I want every possible piece of information for the Markov chain. I'll just rescale by the basic units so we don't have weird numbers. We have integer or like good fraction. And this is so a random sample of what you have got here. So we have this data, the node and the intervals. All the rest is basically just for playing. So once we are here, we have to decide. We want to create a Markov process with this. So we need observables. And I chose the most obvious ones as observables. So the length of the nodes, and the position of the nodes in the song. So length of a node, let's take out the length sequences, and we have like what, 10, 15 different intervals. We can create a transition matrix, and we can use the built-in Mathematica capabilities to create a Markov process out of a transition matrix. And of course, we can visualize some properties of the Markov process, like the transition matrix we just built, of a limit transition matrix. And we can visualize, I've built a little graph here to visualize. So where we are, the redder the arrow, the more probable is to go from one with the positions, or length, one length to the other one. Then we have nodes. We can create a Markov process also for nodes. And this is what we go. This is a bit more difficult to follow. And we have positions. So positions will work roughly the same way. Have a position in the bit. And this is where we go. So now we want to create a global Markov process. And first try, let's combine nodes and position. So we create a bigger transition matrix. We have roughly 1,300 states. We create the transition matrix, we create the Markov process, and we visualize the Markov process. So this is the graph. So we can pick an initial condition, will be like the first notes in the song. Oh, sorry, I forgot to tell you. How do we define our observables? Just one note or one note plus position. We want to link the notes in the song. So here I'm taking group of 2 notes as elements of the Markov process, and I have superposition of one node. So I'm going from basically one node to the other. And so if I stay here in the graph, I will have a starting position, that are the first 2 notes of a song, and at every turn, I will pick one of the branches with the probability that I inferred from the original Bach song. So once I have this, I just have to simulate the song. So here I define a random function that takes the Markov process, and I want a single path of this Markov process. Let's create this, and let's create the song. Hope it will work. Yes, it's working. So this is a probabilistic version of the same song that we have listened to earlier. I mean, it makes no sense, but it's not terrible, I would say. I mean, one note after the other makes sense. Of course, a song is not a Markov process, so and it's better this way probably. And we can see what we are lacking here. We have short-term consistency. We don't have long-term. Of course, this is something I may. Oh, so have to generate the song. Sorry, this is empty. So this was the second part. Don't look. Up. Okay. So I'll just create here 10 random songs to show you what I mean. So the first one is Bach song. There are all the bits. I've separated the bits in the song. So we lack this long-term idea. I mean, this is the song. This is what's happening. And this is completely random. So if you take a small, the point here that a small subset is probabilistically the same, but not the whole thing. So let's try to add some more. Here I add notes positions and lengths. Oh, no, not this length. Go back. So let's create a new Markov process. Complete Markov 2 now. So this is the new space where I'm moving in. This is a bit unfortunate. We have these long branches that are basically fixed. I really wouldn't want this, but I'm at the minimum here. I've just taken 2 songs, 2 notes, sorry. so I cannot do less than this. If I take more, it's even more constrained, the problem. So let's create a new song. It's better than the last one, but oh, I have to listen to this. Songs 1. Sound. What sound? I think so. Yep. Let me take this. Oh, no. What have I done? Okay. Apparently, I'm not a friend with full screen here. Oh, we are here. Okay, sorry for this interruption. And this will be songs 1. Okay, let's try. Who's back on part? Me. Okay, not much better, but I tried. So what's here? Let's see. We have basically the same problem, even adding more observable. Haven't solved it completely. I would say there are a bit more region of like similar length. Here there's a clear evolution in the length of the bits, and what here is of course a lot more randomized. So after this, I mean I apologize with you for my bad songs, and I thank you for your attentions.